We're going to talk about the divergence theorem now, which can be thought of as a direct generalization of the flux form of Green's formula. So here the situation is rather simple. We have a domain in 3D that, let's call it U, and it has a boundary, which is a surface, and a closed surface. So we don't want to have any boundary of the boundary, which would have been, for example, the case if you had a hemisphere. So, and we suppose that we have a vector field F, which is defined all around the domain. Again, it just needs to be defined inside the domain and on its boundary. The boundary will be exclusively oriented with the outward normal. And pretty much what we're saying here is that the flux integral of the vector field over the boundary, when this is oriented in a with the exterior normal, with the outward normal, is going to be the triple integral of the divergence of the vector field in the interior of the domain. It's pretty much the divergence theorem. And here we should recall the definition of a divergence. So if you have a vector field F, then the divergence of F is defined as the gradient operator dot with F, which is the gradient operator, again, is formally given as the vector that has the partial differentiations as its components, and multiplication of a differentiation by of a function by a differentiation is simply to differentiate the function accordingly. So here you will take the derivative of p with respect to x, the derivative of q with respect to y, plus the derivative of r with respect to z. And that's it. So this is in complete analogy with the formula, with the flux form of Green's formula. And it should be noted that it's also a direct generalization of the fundamental theorem of calculus. This is also true for the Green-Stokes formula. This is true for the fundamental theorem of calculus for conservative vector fields. So it's pretty much widely true for everything we have seen, and they all fall under one umbrella formula, which is called Stokes theorem. In any case, let's see how we can apply this. So let's say that we have a ball. So again, we're going to try to apply it this way. So in our example, compute the outer flux of the vector field let's have some fun here with the definition of the vector field. So let's take x cubed by cosine of z cubed. You see something like this, you're very concerned right away. Y cubed plus e to the x squared, same here. And z cubed minus sine of square root of x. Okay, but the truth is there's nothing to worry about. And I should say what the domain is through the boundary of a unit ball. So when I say unit ball, I mean ball of radius 1 centered at the origin. We don't really need to draw this, but any problem that is done over some sort of domain deserves at least an attempt to draw that domain, no matter how ugly the drawing is. And certainly this is not a pretty drawing that I just did, but let's say this is your unit ball, or my notion of what a unit ball should look like. In any case, the important thing is to find the divergence of f here, and this is where everything simplifies, because this is your p, this is your q, and this is your r. And you need to take the derivative of p with respect to x, which gives you a nice 3x squared. The cosine of z cubed disappears, of course, plus the derivative of q with respect to y, same thing for e to the x squared, it's gone. So 3y squared, plus the derivative of r with respect to z, and again, sine of square root of x is gone. So plus 3z squared. So that's the divergence. Where do we need to integrate this? We need to integrate this in the interior of the domain, which is what? It's the unit ball. So we need to compute 3x squared plus 3y squared plus 3z squared dv in the interior. And how are we going to compute that? So this is what we should note here, that the divergence theorem is not going to compute that for us. It's really the domain. I'm sorry. It's really up to us to compute the triple integral that comes up. So how do we compute the triple integral that comes up? Since the domain is the ball, it's a no-brainer. Go to spherical coordinates. So how do we go to spherical coordinates? So here we have the full ball. So it should be pretty straightforward to set up the bounds. So d rho is going to go from 0 to 1. Theta is going all around from 0 to 2 pi. And again, phi has full range because we have the region above the xy plane and equally below the xy plane. So 0 to pi. Now, what is this function? Well, we know that in spherical coordinates, x squared plus y squared plus z squared is rho squared. So we will have a rho squared. And we need to multiply by the Jacobian, which is rho squared times sine phi. And of course, this integral splits. So we will get the integral from 0 to 1 rho to the 4th d rho. And then we will have the integral from 0 to 2 pi cosine theta d theta. And finally, we will have, I'm sorry, there is no cosine theta. It's just d theta, right? Just dreaming of having a more interesting integral, but regardless, this is interesting enough. And on the first component, we find 1/5 by, since the antiderivative will be rho to the 5th over 5. On the second one, we find 2 pi. And on the last one, the antiderivative is negative cosine phi. I think we've seen plenty of times a computation of this type. It's going to give us a 2, making the whole integral 4 pi over 5. And to just convince yourselves that we did something, quite useful, try to compute the corresponding integral of the outer flux directly for the vector field that was given to you. And then you will understand why what we just did is such a big shortcut. It allows us to pretty much minimize the work that we would have otherwise needed to do. And that's, thanks for watching.